Yeah, I'm Keith Vertanen, and for a change of pace, I'm from Michigan Tech. And so this is work with my awesome and hardworking undergrads, Dylan, Crystal, Alex, and Robbie, as well as with my collaborator, Kristensson. And so the overall motivation of this work was basically to look at text entry for challenging input. So I think we can all relate to sort of you're typing on your phone and you sort of, everything's going fine, and then you know something's about to go wrong, right? You've got a difficult word and it's going to be trouble. And so this whole study is all about sort of what kind of interface interventions can we add to sort of help people to either preemptively avoid those recognition errors or to correct the recognition errors once they occur. And so kind of our first problem in this work was sort of looking at, we want to have errors, right? And kind of a typical problem is the phrase sets we use are actually really predictable under a well-trained language model. And so kind of our first step was to look at, let's get some harder phrases. And so making it harder, part one, what we did is we went to Amazon Turk and collected a bunch of sentences. And what we did is we picked out sentences that had a out-of-vocabulary word with respect to the 100,000 word vocabulary used by our decoder. And so our decoder can still infer these words, but it's actually a lot more difficult for it to do so. And we had them validated by Amazon Turk workers to make sure they were sort of easy to understand and that workers could remember these words quite easily. And in all user studies I'm going to present, basically people are going to enter, half the phrases are going to have an out-of-vocabulary word, and then half of the phrases will have no out-of-vocabulary word. And you see on the bottom some examples, like in vocabulary, things like I'm prettier than you, or woke up still loving y'all. And things that are out of vocabulary are things like ready to meet Nanook and I voted for Brexit. And these are all in our supplemental materials or available from my website. Making it harder, part two, we're going to do this on a smartwatch. So we think a smartwatch is a good test bed for looking at like future-looking text entry interfaces. So it's very noisy because it's a really small sensor. And then we're also going to do the decoding. We're going to use our VelociTap decoder from Kai 2015. And so this decoder is actually quite accurate, but when you try and fit it onto a smartwatch, the main constraint is that we really have to prune the language models. And the language models are now pruned to a regime where we're actually making search errors. And the touch model on our decoder is also quite simple. We're basically using the same 2D Gaussians across the whole keyboard. There's sort of no cleverness in the touch model. First research question was, can users anticipate these difficult words? Do they know a priori that something's going to go wrong? And so we designed a really simple interface idea that we could have people dwell-click on particular letters that they didn't want to be subject to probabilistic decoding. And I'm going to show you a video that's going to basically voice over and describe this. But the first experiment is going to be sort of a within-subject design with 16 participants, and they're either going to be able to use this feature where they lock individual letters, or they're going to be forbidden from using the feature. Okay? And let's hope this works.
This video shows experiment 1's interface. The keyboard has the letters A through Z plus apostrophe. As I tap, the nearest key is added to the text area. Swiping right replaces the nearest key with the most probable text. For a long tap, the nearest key is shown in a large font. In the no-lock condition, all letters are probabilistically decoded regardless of tap length. Here the word Sevco was misrecognized as Seiko. In this experiment, we did not allow correction of recognition errors. Here's experiment 1's lock condition. The interaction is the same, except now a long tap causes a particular letter to be locked. When a letter is locked, the color of the large letter shown over the text area changes and the watch vibrates. In this example, the first half of the name Nakart was tapped quickly, while in the second half, each letter was locked. The word has been successfully recognized.
Okay, so that was our first experiment, and here are some of the results. So I'm showing the error rate on the graph on the left. I've got the character error rate on the y-axis. And so we did see a significant reduction in the character error rate with the lock condition. So when they were locking, they got an error rate of 3.3%, and in the no-lock condition, it was much higher at 6.2%. But as you might imagine, doing this locking, we had to wait 500 milliseconds in order for the lock to trigger, and this did cause a significant reduction in entry rate, and we went from 23 words per minute in the no-lock condition down to about 21. So there's a small hit in total corrected words per minute performance. Our next question was, that was very basic keyboard, so all your keyboards normally have these prediction slots above them. And there are actually a lot of choices about what you could put in those prediction slots to help people either avoid errors or correct errors once they've occurred. And we wanted to basically look at what are the different design possibilities for this. And so we're going to run a computational experiment as experiment 2, and we're going to run a simulated user on 3,000 sentences typed by people in various past studies we've run on small form factor keyboards on touchscreens. And we're going to vary the number of prediction slots available from 2 to 6. And then we're going to try all possible ways we can use 4 different distinct types of predictions. The first is prefix completions. So this is assuming your noisy taps represent the prefix of a word. So maybe you type TH and it's predicting the word there. Or maybe your taps represent the entire word. So if you only had 2 taps, it would only predict words that more or less had 2 letters in them. Third type is kind of a hybrid of the first 2 types. So likely slots either are prefix completions or they're best recognition alternatives according to the probability under the model. So they can be either, and so they tend to be maybe prefix completions in the beginning of the entry and then converge to recognition alternatives as you type more text. And then the final option, you can either have this one or you don't, which is basically a literal slot, which is exactly the keys you type with no sort of probabilistic inference. And this was offline, and so here's a scatter plot of all 135 different designs. And so general trends you can see, so on the y-axis I have keystroke savings, and that's basically a measure of how many keys you're saving when you're typing. So it's some kind of measure of acceleration potential for the design. So we want higher keystroke savings, and on the x-axis we have character error rate, and we want a lower character error rate. And so this is showing how good you can get using optimal use of a certain number of prediction slots. General trends to note, as you use more slots, as you might imagine, you get better in both metrics, though gains start to diminish past 5 total selection slots. And then the other trend to note is you've got this group that's got a low keystroke savings, but some of the best character error rates. And these represent designs where we're using all of the slots for recognition alternatives. And you're seeing some residual keystroke savings because our simulation used prefix completions in sort of the case before they started tapping for a particular word. So that's why you're seeing that. And this led us to the design we're going to talk about for the second 2 user studies. And you can see the complete table in our supplemental materials, but I'll just highlight the 2 we chose. So we decided on a design for VelociWatch that involved 5 selection slots. And again, I'll go show you a video that will explain this in more detail. But we're going to surround the main text entry area with 4 prediction slots, 1 literal slot, 3 likely slots, and then we're going to put the best recognition hypothesis in the center area. And we're going to compare that in our final user study against a much simpler design where we only have 2 slots. In this case, we're going to have a literal slot and we're going to have a likely hypothesis. And this is similar to WatchWriter interface that was in Kai a few years back. So once we had that design informed by our computational experiments, what we wanted to do is test it out. And one question we had, we were worried that basically these really small prediction slots, remember this is all on a smartwatch, we were worried that people were going to have trouble tapping these really small prediction slots, and then they would have errors while they're trying to fix errors, and that's never a good thing. And we decided we were going to test. You could tap these slots, but how we kind of designed them, you could imagine swiping in diagonal directions to select the different slots. And in our third experiment, we're going to have 24 participants do 3 different conditions. They're either going to have to tap all the slots, they're going to make swipe gestures for all the slots, or they're going to do a hybrid where they use swiping for essentially the space bar and doing left swipe to do a backspace. And again, I'll show you the video will explain it more.
This video shows experiment 3's interface. The user has currently typed is followed by Oz. The one best recognition result is shown in the text area in reverse video. The top left slot has the literal input Oz. The other slots surrounding the text area have the 3 most likely other hypotheses, Ox, Is, and Ozzy. A backspace button is on the left. In the tap condition, all prediction slots had to be selected by tapping on them. In this experiment, recognition errors could be corrected by using the backspace feature. As a word was erased using the backspace, the prediction slots update themselves to reflect the best hypotheses given the remaining text. The user in this case is trying to enter, "Is Ozzy still the bad guy?" The last word has been misrecognized several times before the user finally successfully obtains the word guy. Here the user is typing, "Weezer is still very relevant." In the swipe condition, users swiped right to select the one best result, swiped left to backspace, and swiped diagonally to select the other predictions. The user here swiped up and left to select Weezer, then swipes right to select several one best results, and then swipes down and right to select relevant. Here the user is typing, "My Snapchat is pointless." In the hybrid condition, users swiped right to select the one best result, swiped left to backspace, and tapped to select predictions. In this example, the recognizer mistakenly inserted a space between snap and chat. In all conditions, users could lock letters by long pressing. Here the user locked P and C in order to successfully obtain Snapchat. The user then taps in the upper right corner to select the prefix completion pointless.
All right, so here are the results from that user study. And we're seeing on the graph on the left, we see the entry rate of the 3 different conditions, and pretty much the entry rate was the same. We have an entry rate of 17.7 words per minute in tap, 17.8 in swipe, and 17.4 in hybrid. This wasn't significantly different. And error rates were also similar with 3.2% in tap, 3.4% in swipe, and 2.1% in hybrid. And subjective feedback was sort of mixed. Some users like to swipe, some users like to tap. And so in our final experiment, we're just going to allow them to do any. So this is kind of, we're a little surprised by this, right? We thought the swipe thing would be an advantage. And in fact, they were actually pretty good at tapping these small selection slots. Okay? And our final study, research question we're interested in here is, how does this compare to a simple one, right? Now we've got a pretty complicated keyboard running on a smartwatch, right? We've got the 4 prediction slots plus the best result in the center. You can delete a character. We implemented a feature so you could delete an entire word at a time by a long press on the backspace button. And let's compare it against this much simpler keyboard. And this is going to be, again, a within subject. We're going to compare basically VelociWatch against what we're calling 2-slot. And again, I'll let the video virtual Keith explain it.
This video shows experiment 4's interface. Here the user is typing, "Just went on an unfollowing spree." The VelociWatch condition was similar to the previous experiment, except that we allowed users to swipe or to tap in order to select the prediction slots or to backspace a character. Users could lock individual letters by long pressing. We also allowed users to delete an entire word at a time by long pressing the backspace key. In this example, the user is typing, "Thanks, TRICARE, for dropping the ball." The 2-slot condition had a simpler interface design. This keyboard only had 3 options above the keyboard. The left option was the most likely word, which was either the one best recognition result or the best prefix completion. The center option was the literal input. The button on the right erased the entire word. The 3 options had to be tapped. In the 2-slot condition, there was no way to delete individual letters. If an error was made, a user had to delete the word and simply try again. This condition did not allow letters to be locked and did not show a preview of the current nearest key during touch events.
Okay, so you ready for the surprise result? Okay, so normally this is the part where I say VelociWatch was awesome. So here are the results. And so it turns out this 2-slot was actually faster. And so focus maybe on, focus on maybe the all results here. And VelociWatch, we had an entry rate of 17.3 words per minute, and 2-slot was significantly faster at 20.6. And this held both for the in vocabulary as well as the out of vocabulary phrases. The error rates were similar in both conditions, so 3.0% in VelociWatch and 3.0% in 2-slot. And kind of the remarkable thing about this is, if you paid attention to the 2-slot video, those hard words were not probably going to get predicted right. And what people were doing, and you can check the paper for more results, is basically they were using that literal slot, which meant they typed every single letter of that difficult word completely correctly on the smartwatch without making any mistakes, because if they made any mistakes, they had to start the whole word over. Despite that, they ended up being faster in that condition. So a lot more results in the paper, but key takeaways. If you're looking to do sort of error correction stuff in text entry, we've got a challenging phrase set which will help you have more errors so you can have more fun in your text entry experiments. We think this letter locking feature is actually, it's really obvious. People got this right away. It took almost no training. And interestingly, you can also see the paper. It was interesting to see some people lock some letters or all the letters, and people are actually doing some clever strategies about what specific letters they locked. And they have a pretty decent idea what might go wrong in a probabilistic decoder. Tapping or swiping the slots, we found there was no real difference here. And so our advice would be maybe enable both of them if you have an interface design where that makes sense. And our surprising result is that simpler design outperformed a more complex one, and so maybe it would require more training for the users, or maybe the cognitive overheads just trump the gains we get from having the more fancy prediction slots. And the real surprise to us was people could do 21 words a minute in this simple interface at a low error rate on a smartwatch on some pretty difficult text. Okay, thank you.
Okay, we can still have questions because the tech notes weren't your fault.
Okay, get started? Okay. Keith, thank you very much. You jam so much always in one paper. So I'm not sure what the take-home message is anymore. But first of all, clarification. Lock means long press on one key for the rest of the word, or for every letter you have to unlock?
Yeah, so we implemented on a per letter basis, so you locked individually. And you can actually see, so I'll show you this backup slide. On words like sort of Brexit, this person locked only the X key. So they could go sort of fast and then lock and then go back to fast, or they could...
And the lock has a pop-up key to...
Yeah, so you would dwell and you'd see the pop-up, so you could do a correction and move your finger and correct.
Standard way of doing it.
Yeah.
Okay, so the second question is why the last results were surprising in consideration of your first or second the computational experiment that shows the curve of the more slot you offer, the sort of higher performance you get.
But we got lower performance with more slots.
Right. So is your point that's a contradiction or that's consistent from the?
No, it's a contradiction from that result.
It's a contradiction.
Right? Okay. And so what I think that computational thing didn't model was, one thing it doesn't model is cognitive overheads. And sort of like I like the first paper where they did the dynamic suggestion thing. We weren't doing that. We were popping 5 suggestions at every key press, right? And so the cognitive overheads of looking at that, and we talked to participants, and they did sort of say I like, the ones that they were mixed in which one they liked, but the ones that liked the simpler one just didn't like to look at all those things, right? And it takes time to look at those things. So I think the model should, a computational experiment maybe should model that.
Yeah, it's very interesting. I guess the overall message is that it's just full of surprises. Like we did in WatchWriter. Frankly, we didn't believe initially. We thought it's got to be crazy. You want to put a keyboard on a watch? That's got to be crazy.
Yeah.
But when we did, we were literally surprised ourselves. And it's also the simplest design seemed to just work fine. Yeah. It's actually the most, in a way, that in hindsight, the most obvious design given a small amount of space. But still surprising. Yeah,
it's surprising, and I think, maybe the surprise is the fat finger problem is, perhaps a little bit overstated, right? At least for this population, very, stable, very young and techno-efficient people.
Don't underestimate either human intelligence or machine intelligence. I think that's
one here and then over there. Here first.
Hi, this is Yu Jungko from Stony Brook University. Thank you for your great work and talk. And I'm wondering because the simplicity is already worked pretty well. And the gesture with engaging for the swipe. I'm considering whether there's more complicated gesture can evolve into your design, or if it's not, then why?
So let me understand. So the question is, have we thought about doing shape writing? In this interface,
not like shape writing. More maybe you can rotate it, you can delete the key character by character, or because swipe is just
Yeah, I think that's so if you have, the correction thing, I think, is maybe part of this story that we don't understand is the simple keyboard had like this, you could delete an entire word at a time. And I think a lot of our time in VelociWatch is people like swipe, 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 delete, 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 and that's very time consuming. So I think, yeah, more sophisticated, if that's your question, is, yeah, like thinking more through like sort of that and speeding that aspect might be good. I think there's a hybrid design between these two that's, probably better than either of them.
Thank you.
Keith, thanks for the talk. Alan Hines in Bell Labs. Were you able to see any difference in results between complete novice users and relatively expert watch typers?
Right. So we asked that question, and I would say my recollection is almost very few participants reporting ever having used a watch. All reported using touchscreens, obviously. And so I don't think, we don't have enough data points to say, like, the differential in performance of watch experts versus non-watch experts.
Right. And then related to that, did you see any improvement in VelociWatch with time? In other words, people kind of have a natural, nowadays, inbuilt capability for tap typing. But did you see any increase in VelociWatch over
and
time?
I think that's, future work, basically. Like, we only were doing hour sessions here, and so I didn't feel like, in a lot of cases they're doing 10 or 12 phrases, and I didn't bother look at a learning curve there because I don't think it would be that meaningful. So I think it's a great question, and I think I'd like to see, maybe if they just had enough time, VelociWatch would be faster, right? But yeah, we haven't sort of run a longitudinal. But it's a good idea.
Thank you again, Keith.